Greetings. My name is William Oliver. I'm a professor of electrical engineering and computer science, a professor of physics, and a Lincoln Laboratory Fellow, all at the Massachusetts Institute of Technology. It's really a pleasure to be here to speak with you today. And I'd like to talk about the subject of quantum engineering of superconducting qubits, as well as activities that are ongoing in the quantum computing space at MIT. Before we get into quantum computing, though, I think it's useful to go back and look at the history of classical electronic computing. If we go back to early 1900s, 1906, the vacuum tube was invented. It was used for radio transceivers, but it was a good 40 years before it found its use in a computer called ENIAC, developed at the University of Pennsylvania. And you're probably familiar with this photo, and the computer takes up the entire room. Now, around that time, the transistor was invented at Bell Laboratories. And although within about 10 years, we had a fully transistor-based computer called TX0 or TIXO, developed here at MIT and at Lincoln Lab, it didn't look anything like the circuits that we associate with computers today. To get there, of course, we needed the invention of the integrated circuit in the late 50s. But even then, you'd have to advance into the 70s before we saw circuits like this one, the Intel 4004, with about 2,000 transistors, just a 4-bit processor. It took another 25 years to get to the Pentium Pro with millions of transistors, and then another 25 years to get to where we are today with multi-core processors, billions of transistors in processors as well as GPUs. So from this standpoint, looking back, from the initial demonstration until now, it's well over 100 years of development. We can compare with that quantum computing, which is far more nascent. In the early 1980s, Richard Feynman, Uli Mannin, and others suggested that if you want to simulate or emulate a quantum system, you should use another quantum system to do that, because there are just too many degrees of freedom, and it's difficult for classical computers to keep track of all that information. And so theorists thought about how to take advantage of such a quantum computer. And in the mid-90s, we started to see algorithms like Peter Shor's factoring algorithm, Eddie Farhi's adiabatic quantum computing, Nishimori-san's adiabatic quantum annealing algorithm, Grover's algorithm, and also error correcting codes were first developed at this time, theoretically. In the early 2000s, we factored 15, Ai Chuang and collaborators factored 15 into 3 times 5. So we saw that these algorithms can work on very small scale quantum computers. And then fast forward 20 years to where we are today, where we have quantum computers in the cloud from IBM and others, and even initial demonstrations of quantum advantage. So the takeaway message is this: quantum computing is real, and it's transitioning from scientific curiosity or from the lab to technical reality. But as engineers, we know that advancing from discovery to useful machines will take time. And of course, it takes a significant amount of engineering development. And maybe another takeaway is that you should be in the game if you want to play. It's perhaps no surprise that many of the players who are making these chips today were in it for several decades before they were able to make these chips. Okay. So if we look at commercial quantum processors that are available today, here's a processor, Sycamore from Google. Here's one of IBM's earlier quantum processors that are in the cloud, Righetti's quantum processor. These 3 are superconducting. Here's one from IonQ, which is a trapped ion company that I'm sure you've heard of. And this one is the D-Wave quantum computer, which is a quantum annealer, a different type of quantum computer than these other 4. This here, of course, is not a quantum computer. You'll probably recognize this as the Wright Flyer, the first manned airplane to be self-propelled and fly. And I view this as about the level that we're at today. An amazing achievement. It's a milestone. But this Wright Flyer, it flew about 600 feet. It certainly is viewed now as the dawn of aviation. And I think many of these computers will be viewed as the dawn of quantum computing. But there's a lot of promise to quantum computing, and to realize this promise, we need to engineer quantum systems that are robust, reproducible, extensible, and in fact useful. Right? And that's what I would like to tell you about today and the activities we're doing here at MIT. So with that, I'll give a brief introduction to quantum computing. We'll then look at some qubit modalities that we're studying, and then engineering quantum systems. And I'll tell you a bit about my own research. So to understand how a quantum computer is different, I think, again, it's worthwhile to compare with a classical computer. The classical computers we use today are based on bits, Boolean logic. Often that's a transistor. The transistor state can be 0 or it can be 1. Those are the only two options. These are discrete states. There's almost never an error, maybe 1 part in 10 to the 20 or better. And so measurement is deterministic. If I set it in 1, I'm going to measure a 1. If I set it in 0, I'm going to measure a 0. Quantum computers, though, are different. And they're based on quantum bits, or we call them qubits. And these are coherent two-level systems. And a way to think about it is to look at this sphere, which we call the Bloch sphere. But you can think of it as the planet Earth. And the North Pole is state 0. The South Pole is state 1. And if you're at the North or the South Pole, you're just a classical bit, right? But of course, we can be anywhere else on the surface of the Earth, not just the North and the South Pole. And when we're anywhere else, we're in a quantum mechanical state that's called a superposition state. It's a superposition of quantum state 0 and 1 simultaneously with weighting factors that we'll call them here alpha and beta. These are quantum mechanical superposition states, manifestly quantum mechanical. And one consequence is that the measurement becomes probabilistic. So if this state were on the equator with an equal weighting of 0 and 1, half of the time we make the measurement, we'll get 0, half of the time we'll get 1. And that's completely random which one we'll get. So this has consequence for how we encode and use quantum information, and it's fundamentally different than classical computers. To see that, let's consider now again our classical bits, and let's say that we have n of them, and we know that we can represent an exponentially large number of states, 2 to the n. So if n is 3, that's 2 to the 3 or 8 different states. But classically, we can only represent one of them at a time. It could be 0, 0, 0 or 0, 0, 1 all the way up to 1, 1, 1. And so if we want to process information and calculate an output, we basically have two choices. We can either take our input, say 0, 0, 0, and put it into our classical computer and get an output. And we can do that either serially in time, or we can create copies of the hardware and do it in parallel. But either way, if there's an exponentially large number of states, it will take either exponential time or exponential resources. Now, a quantum computer, again, we can have n qubits, and there's still 2 to the n different ways that we can arrange those qubit states. But the difference is that we can now put all of them, maybe call them aspects. We can create all aspects in a single superposition state with weighting coefficients, and they're 2 to the n weighting coefficients. Now, what this leads to is a quantum version of parallelism, and in fact, also quantum interference, a manifestly quantum mechanical effect. And so you can think of this as taking a large superposition state, putting it into a quantum computer, and getting a large superposition state out. And how we use that, I'll talk about in just a moment. So again, quantum computers rely on encoding this information in fundamentally different ways. And so how can we take advantage of it? Well, what we do is we run a quantum algorithm. And so we take this massive superposition state, often we'll make it equally weighted. So all of these aspects, all 2 to the n are equally weighted. We'll put it into a computer and we'll run an algorithm. And an algorithm is comprised of single qubit gates where we apply one pulse to one of these qubits, but in fact, it manipulates the coefficients on all 2 to the n aspects in this single state. And that is the concept of quantum parallelism. That's followed by quantum interference. And the net effect is that we've now changed the value of all 2 to the n coefficients in this superposition state. We also have 2 qubit gates, or coupled qubit gates as we call them, where the state of qubit 1 determines the rotation that happens on qubit 2. And again, this is one operation applied now to 2 of the qubits, but it impacts all 2 to the n coefficients in that superposition state. That's also followed by quantum interference. And at the end of the day, the goal of an algorithm designer is to ensure that almost all of the weighting, or ideally all of it, sits in front of one of these aspects only, and the other ones are 0. And the reason for that is that when we make a measurement, it's probabilistic. And the probability that we get any one of these aspects goes as the magnitude squared of the coefficient. So if the coefficient is 1, then with probability 1, we will get this answer, and that is the answer to the question we've posed. And so it behooves, the algorithm designer to design these single and 2 qubit gates in such a way that we go from an equal superposition state at the beginning to having all of the weighting in front of the right answer at the end of the day. And that's the challenge for the algorithm designer. So what are the ingredients to achieve quantum advantage with a quantum algorithm? Well, first, there should be no fast classical algorithm. If there is, we should just use our classical computers because they're very, very good. The second is that we should have a known fast quantum algorithm. We need to develop that, of course. And then the third is that we'd like this to address a useful problem. And so to date, the overlap of these 3 regions is rather small, where useful quantum algorithms exist as we know it today. And this is an active area of research where people are constantly trying to expand this region. And there are 2 types of quantum advantage that we can achieve with a quantum computer. And they're represented here by this equation where there's a prefactor, a polynomial, call it a to the n, or a is a function of n. And then there's an exponential part where the n is in the exponent. And n represents the system size, the time to solution, basically the resources of the problem. So one type of improvement is that we can improve the prefactor. And this is called a polynomial improvement. So for example, if n goes to the square root of n, that's a quadratic improvement. And an example of that is Grover's algorithm. On this side, of course, is exponential improvement. And what that means is that we take n from the exponent and bring it downstairs. So if 2 to the n becomes, for example, n cubed, then that is an exponential improvement. And that is a very, very substantial improvement. To gain an idea of this improvement, we can think about this game here to represent exponential growth. And the idea here is that your boss comes to you and says, let's say this month I'm going to pay you in the following way. I'll either give you $10 million or I'll pay you in the following way. On the first day, I will give you 2 to the first power pennies, so 2 pennies. On the second day, you've earned 2 squared pennies, so that's 4. On the third day, 2 to the 3, which is 8 pennies, etc. And after 31 days, would you rather take all of the pennies on the 31st day, or would you take $10 million? And of course, you think about this and it's, okay, maybe 16 pennies and then 32. And because we don't experience exponential growth every day in real life, we think $10 million sounds pretty good. But of course, you would have lost money doing that because just on the 31st day, you would have $21 million, right? And that's a huge number of pennies. And this represents the power of exponential growth. So if we look at that in terms of the amount of data that a quantum computer can represent in this superposition state, if you have 30 qubits, you would require basically the memory in a laptop to store that amount of information. If you have just 50 qubits, not even doubling that, now you need a supercomputer to store all of that information. At 80 qubits, we now need all of the computers on Earth and their memory. At 160 qubits, now we need every silicon atom on Earth to represent a bit of information. And then at 300 qubits, it's now more than all of the atoms in the known universe. Again, this is just another way to express the power of exponential growth. Okay, of course, we need to learn how to take advantage of this. So there are a number of algorithms that have been developed over the years, and I highlight here several categories of algorithms. I won't read the whole chart, but just to say that many, if not all of these algorithms have been either developed or substantially advanced by faculty here at MIT. And the key ones are in quantum simulation, so simulating a system, such as quantum chemistry. Of course, factoring, that's Peter Shor's algorithm, or other number theoretic algorithms. Linear systems of equations, sampling solutions when the matrix gets very large. Optimization problems, and of course, Grover's search algorithm. And you can see for many of these, there's an exponential speed up. Grover's is polynomial. Optimization, it depends on how you define the optimization problem, what the speed up is, and it's currently, being established. And of course, there are limitations to this that we are working on all the time to improve these algorithms. So why don't we have quantum computers today? Well, there are two time scales that we care about. One is the coherence time, and that's the qubit's lifetime, how long it remains valid, basically. So at time t equals 0, we can put our qubits in our quantum computer in a quantum state, but it's constantly interacting with its environment from that point forward. And over time, the state begins to blur and eventually disappears. Now, the qubits are still there, but the state that they're in after this time becomes completely unknown to us due to the interactions with the environment, which we just can't keep track of. And the time scale over which this occurs is called the coherence time. The second time we care about is the gate time, which is how long does it take to do a single gate operation, whether it's a single qubit or a 2-qubit gate operation. It's a typical time. And the figure of merit, as you might imagine, is how many gates can I implement within that coherence time? The more gates I can do within the coherence time, the larger the algorithm I can perform. And this is a proxy for a more rigorous metric known as benchmarking metric, known as fidelity. And I'd like to point out that long coherence times alone are insufficient, right? It's how many gates you can do before an error. Okay, and so with this, we can compare different modalities against one another. And on the vertical axis is this metric, the number of operations before an error. On the right axis is the corresponding gate fidelity. And you can see that one error in 100 is basically 99% fidelity. One error in 1,000 is basically 99.9% fidelity, et cetera. And on the horizontal axis is gate speed. And of course, faster is better. Now, this dashed line that just appeared is the most lenient threshold for quantum error correction that we know of. It's approximately the most lenient threshold. And of course, we want to be above this line for quantum error correction to actually improve the robustness of our system. So the fidelity needs to be higher than this dashed line for quantum error correction. And in the upper right corner is where the best performance is. Now, with this, we can start looking at different candidate technologies. And we look at the ones that can do single and 2-qubit gates because this allows us to form a universal set of gates to perform any arbitrary quantum logic. Now, some of these that I've indicated here as having done single qubit gates have also now in silicon done 2-qubit gates, and they're working on benchmarking those gates. And others have done benchmarking of the gates, and they're shown with the ovals. So the two leading candidates today are trapped ions. Here are some of my colleagues doing those at MIT and Lincoln Lab, as well as superconducting qubits, my own researcher and my colleagues. And in a nutshell, trapped ions are trying to make faster gates, higher 2-qubit gate fidelities, and superconducting qubits are trying to make higher fidelity gates. They're already pretty fast. Other technologies that are up and coming, neutral atoms. Here are some colleagues at MIT working on those, as well as NV centers and my colleagues as well. Now, NV centers can be used for quantum computing. They're also great as magnetic field sensors. And my own group, I should say, is also starting silicon quantum dots since this past fall. So there are many candidate technologies here under development to realize the promise of quantum computing. And I should say this was from circa 2019, a couple of years ago. And since then, all of these numbers have improved by about a factor of 10. Okay, so a couple of years ago, almost just over 2 years ago, there was a demonstration of quantum advantage. I'd like to just talk through what that means. So this was done by Google with their Sycamore chip, had 53 qubits. The 54th one was out of spec. And it had tunable couplers between each qubit that you could then turn on the 2-qubit gates. And the experiment went something like this. You have all of these qubits in the array, and you'll do a series of single and 2-qubit gates on it. and then repeat that over and over, and you randomize these gates. And as you increase for a fixed sequence the number of qubits that you consider in your array, it gets harder and harder for classical computers to simulate that. So what they did is they looked at the full circuit with n qubits. They looked at what they called an elliptic circuit, where it had the same number of qubits, but the connection between two halves was simplified. And then a patch circuit where the connection between the two halves was completely broken, right? And so it's easier to simulate half of the qubits than all of them. And what they saw is that they got identically the same benchmarking fidelity as they increased the number of qubits, and it continued on and on. And even at this all 53 qubits for this simplified structure, it took 5 hours on a classical computer to do it, okay? They then went into the quantum advantage regime, where they're now using all 53 qubits, they're using a hard set of gates, and they're implementing it and increasing the number of repetitions or cycles of those gates. And what you see is it gets harder and harder and harder for the classical computer to solve it. In fact, they didn't even try, right? They just used the quantum computer to do it, as well as looking at the patched and elated versions, which they could simulate. And so it was later found out, they initially said 10,000 years, but it was later pointed out by IBM that if you use all of the resources on the #1 computer in the world, Summit computer at Oak Ridge National Laboratory, that, okay, maybe it takes a couple days, because it's a different algorithm. But still, in my opinion, this is a very important demonstration of quantum advantage, because what they showed is that with 53 qubits, they could, in about 200 seconds, calculate a random number, and doing the same algorithm on the Summit, the best supercomputer in the world, it would take a few days or more. And in fact, on the Summit computer, remember, there's 40,000 processors. That's 10 to the 17 transistors. And it would take hundreds of megawatts of power to run that computer for days, right? Whereas Sycamore, it was 53 qubits, 200 seconds, maybe 100 kilowatts of power, right? And then there's also 10 to the 17 bits of memory as well, okay? So when you think of it in these terms, this is a substantial savings doing this task on a quantum computer. Now, of course, what's important is to now find tasks which are commercially viable to run on a quantum computer. Okay. So to do that, we need to think of architectural layers of a quantum information processor. And I use this one from Cody Jones here. The physical qubits are at the bottom. The application is at the top. And in between, we see 3 layers which are reminiscent from our classical computers. Of course, there's a logical controller. There's error correction. We use error correction sometimes in memory, for example. And then there's also this passive error suppression, which is an open loop correction technique. And in a quantum computer, on every clock cycle, what the logical controller will do is, of course, implement the algorithm on the physical qubits, but it's also going to implement passive error suppression and also active error correction. It's going to look for errors, and when it detects them, keep track of them and fix them. And this happens continuously throughout the computation, right? And by doing quantum error correction and passive error suppression, we can make the lifetime of the computer for the application longer than the individual lifetime for the individual physical qubits. Yeah, so that's important. So with that, let me just briefly talk about where we are in achieving this with my own research here at MIT and Lincoln Lab. So I work on superconducting qubits. This is an SEM image of 5 superconducting qubits in a row, a zoom in on one of them. And these are called transmons, this particular variety. This is basically fabricated in the same way that we fabricate silicon devices. It uses the same facility. It's fabricated on silicon wafers. And this plus sign is a capacitor. And then the Josephson junctions that we use as an inductor are down here, and it's basically an LC resonator that's anharmonic. There's control lines coming in from the bottom and readout coming from the top. If we look at coherence, our coherence times are around 100 microseconds. And if we do our fidelity benchmarking, we have almost 3 nines, 2 qubit fidelity, and more than 3 nines, 1 qubit fidelities. Now, of course, what we're currently doing is not just one-dimensional arrays, but two-dimensional arrays. And this is our largest chip so far. This is 4 by 4 qubits. Each one of these represents a qubit. And what you can see is things are getting pretty crowded, as you might imagine. There's a lot of wires coming in from the edge. And then we even need some long wire bonds to actually access some of the functionality in the middle. And we know that this is not extensible, right? To make an extensible processor, we need to have 3D integration. And so I'd like to just show some pictures of work that we've been doing over the last few years to realize these 3D integrated structures. Before I do that, let me just mention that we are building at the MIT campus a 64 qubit capable quantum testbed made possible by a generous donation from Keysight Technologies. Now, we aren't going to jump right away to 64 qubits. We're going to test circuits like this with 16 qubits, but this will allow us room to grow in the coming years. And to do that, we need to use 3D integration processes. And this was developed by, under a program funded by IARPA for quantum annealing called the Quantum Enhanced Optimization Program. And in this program, what we developed was what we called a 3-stack. Now, the 3-stack is named because we stack together 3 chips. One is the qubit chip, and these are the qubits grown on a silicon wafer. One is an interposer wafer made out of the same silicon. This silicon is basically intrinsic silicon with high resistivity, so it's very low loss. And we use the same silicon for both the qubit chip and the interposer. And then we have a readout and interconnect layer, which has multiple wiring layers to help route signals around. Now, some features of this approach is that the qubits have what we call a large mode volume. So the electric field on this capacitor indicated in red, and these are the field lines, they extend into the silicon wafer, which has very high Q. And so the damping of the circuit is minimized. We also gain an additional layer, the top layer of the interposer, where we can put things like qubit to qubit couplers. And of course, importantly, we had to develop through silicon vias to bring signals from the routing layer up to the qubits. Now, we did this so that we could fabricate these 3 chips independently. This allows us to maintain process independence for each layer and then combine them together. Now, someday we may learn how to do all of this monolithically, but that's very challenging. And so this is an approach that we're taking today. So where we're at, okay, so here is this say 16 qubit array. And the idea would be that you flip that over so it's face down onto the interposer, and then you use indium bumps to bump bond it together. We've also developed these through silicon vias, which I show here. These have high aspect ratio. They're 10 to 20 microns at the top, but 200 microns deep. So that's about 10 to 20 aspect ratio. And these are superconducting. They're lined with titanium nitride. And so you can see here that they superconduct around 2.5 to 3 Kelvin. That's when they fully go superconducting. Of course, we're operating these devices at millikelvin temperatures. And so that's well into the superconducting regime. This readout and interconnect layer is made, in fact, in this case, out of niobium. I don't think that I mentioned it, but the qubits are aluminum. Our readout and interconnect layer is made in niobium. It's an 8-layer process. It also has active junctions, but those are used, say, for example, in traveling wave parametric amplifiers or in a classical digital logic called SFQ, and that's where this 8-layer process is used. But for our purposes here, we don't really need the junctions at this point. We're just using the vias that you see here to connect different wiring layers and thereby route signals from the edge of our chip, the interposer down, or sorry, through the readout interconnect layer and then up to the chip. But in the future, we can use these Josephson junctions if we need to. And then finally, we use indium bump bonding to connect these different chips together. And these just show some pictures here of alignment. And we achieve a low tilt so that these are fairly planar as a result. So that's just a snapshot at some of the research we're doing. I should mention that we have demonstrated superconducting qubits, 10 of them operating in this 3-stack structure, and I hope to have some publications available on that shortly. So just necking back out, there's a lot of activity going on worldwide in quantum, and I won't read through this whole chart, but I think we know that a lot of government investment has gone into quantum computing. But what's really changed over the last several years is the large number of companies that are also jumping in, and even more so. And so it was in this context that we formed the Center for Quantum Engineering at MIT. And you can find our website here. The mission statement is that we've established an initiative dedicated to the pursuit and practice of quantum engineering to accelerate the development of quantum technologies. And our objectives are to first define quantum engineering. We need to make the curriculum, write textbooks, so that we can train tomorrow's quantum engineers, create a workforce. And to do that, we want to partner with industry via a consortium model. Now, we have several engagements. One of the first things that we did was create a series of courses and a curriculum for professionals, people who are already in industry. And this is through our MIT X Pro program. It was sponsored by IBM, and there are 4 courses, 2 on the fundamentals of quantum computing and 2 on the practical realities of quantum computing. These are online, 4 weeks each. And if you'd like to learn more, either contact me or feel free to go to this website. We also sponsor several fellowships through our center, named the Doc Bedard Fellowship Program, 3-year graduate fellowships. We also have some seed funding and also some funding to develop the quantum engineering curriculum. Doc Bedard was a pioneer in cryogenic computing in the United States. We help facilitate faculty industry engagement, and that includes the industrial group that I just mentioned. Now, as part of our industrial membership group, we have an algorithm program. We believe it's very important to develop algorithms that may have practical use or commercial viability. And so we want to get more students thinking about this. And so the algorithm program through the center and the Quantum Science and Engineering Consortium is basically to co-develop algorithms with companies, with students, and also optionally with Zapata, which is a startup company that focuses on algorithms. So one example of this is BMW is a member of our consortium. And they work together with students as well as researchers at Zapata to develop an optimization algorithm that's relevant. It's a relevant problem to BMW and their manufacturing line. And so we have researchers from each of these locations who meet bi-weekly and discuss and develop quantum algorithms. And the types of research that they do is first, let's find the best classical algorithm that's available. We'll use that as our benchmark. We'll then look at quantum algorithms that can do this task. And then we'll either benchmark them first on a classical computer, then we'll benchmark them possibly on hardware at MIT, or Zapata has access to some of the online quantum computers available from companies like IBM and others. So this is one of our activities. And there are more. Please contact me if you'd like to learn more. Last slide. Quantum engineering at MIT, we're developing curricula around this. And the way that I look at it is it's basically like our institute. There are 2 halves. There's a School of Science and Math, and that's physics, computer science, et cetera. And there's also the School of Engineering. And both sides need to work together if we're going to realize these test beds and future quantum systems. And I view quantum engineering as representing both science and engineering, and it's the bridge that connects these disciplines together. And so with that, let me summarize. Quantum computing, it is transitioning from technical to technical reality. We talked about several different modalities being studied and advanced at MIT. The next steps for commercialization is we need to engineer robust, reproducible machines. We need to expand the repertoire of algorithms that address real-world problems. I talked about our Center for Quantum Engineering and its Industrial Consortium. Please join us. If you'd like to learn more information, feel free to contact me. And I also talked about our professional development courses that we have at MIT, which are great if you have a new team of people who are professionals. They have a professional degree, let's say, but it's not in quantum, and you want to pivot those people into quantum computing. This is a great course to take for that. And so with that, let me thank you for your attention and just highlight the many people at MIT Lincoln Laboratory and at the MIT campus who have contributed to this work, and also our many US government sponsors. And so with that, thank you for your attention.